So in other words, you have, let's say you have some sequence, right? So here's your sequence. That's a series bar. It's just what you get when you add up every term in a sequence. Now, we talked about the sequence of partial sums, right, and trying to get things converging via the sequence of partial sums. But there were a couple of little theorems that we did talk about, which I really want to reiterate today. Okay, so I'll say notes. Some basic notes. Well, first of all, just to make sure everybody is with me. What do I mean by convergent? So if a series is convergent, what does that mean?
Approaches a number.
It approaches the numbers, you add up all the terms, right? If it's divergent, what does it mean?
It approaches infinity.
Or negative infinity.
Or negative infinity.
Or
It
if
doesn't have it.
there's other ways, like the
Or it
suction
oscillates.
cosine, yeah, or the oscillates, right? Good. All right. So you guys are totally with me on this, all right. This is the basic rule of thumb for series. This goes a long way. If you can understand this, it's going to put in perspective all of these convergence tests that we do, and it really will kind of help you. So just do yourself a favor and try and get the gist of this. And I tried to convey it last time. If you have a series and you evaluate the limit and the limit doesn't go to 0, you are guaranteed that it's going to diverge. So for instance, let me do some examples from the current of this.
So those two statements conflict with each other.
No.
Oh.
Question is, does this converge?
I don't know.
No.
Am I supposed to know this immediately, or am I supposed to be able
Well,
to look it up?
I know it immediately. I was kind of wondering if you guys did.
No. 'Cause
Although I did get to know why.
It approaches 5/4.
It does. Do you guys see that? If you were to take this, which is what we're referring to as the AN, what you get is 5/4. Use L'Hopital's rule, but divide through by highest order, top, bottom, 1 over n squared.
Oh, okay. I just use all of them.
So, Showing a series diverges is actually pretty easy. The tricky part is showing that it does converge, because this is where you get wrapped up in the subtlety of the irreversibility of this if then statement. See, what this statement says is that if you have a series which converges, then the limit of that will sure enough go to 0. The problem is not all series who have a generator which goes to 0 and the limit necessarily converge. That's where things get really, really tricky. So,
So, if the limit equals 0,
right.
it doesn't tell us anything.
You're exactly right, and that's why we have all of these stupid
I was gonna
tests.
say,
That
otherwise,
is
what
the-
is the point?
If that were the case, this would be a half-an-hour lecture on series and sequence, and we'd be done. There'd be nothing else to talk about.
Okay.
The problem
So
is
what's
when
the
you,
point
yeah,
then?
when you evaluate the limit, and one that we saw, and, oh, hold on, Lucia, one that we saw already, and I'll go back through today. This is actually divergent. Even though if you take the limit as n goes to infinity, see, this is really equal to 0.
Right.
That's where the problem lies. And because there are so many series that behave like this, all of a sudden we need all of these various litmus tests to start to determine under what conditions does it converge or diverge. Go ahead, Lucia.
So it has a number but it's divergent.
Yeah. That's what I said over here.
Because you're doing the limit, not the
So
sum.
we only need to do the
You're doing
test
the limit, not
on
the sum.
the
If
problems where the
sum
limit
goes to a
equals
number,
0.
it's convergent.
Essentially, right. Because if it's not 0, then it's never going to be convergent.
Right.
See, that's a guarantee that we have. It's not a very big guarantee, but it's a guarantee nonetheless, right?
Okay, so we only need to do the test on when the limit equals 0.
Yeah, that's right. That's right. Because if you ever come across a problem where the limit's not 0,
Then you know it diverges and you're done.
You're done. That's right.
Okay.
The problem is if the limit is 0, it might diverge and might converge. We're not quite sure, right? And that's where all this gray area starts opening up. So that's where we start invoking things like the one test I did discuss and I'll talk about again is what's known as the integral test, right? That's a test that allows us to determine, depending on the structure of the series itself, whether or not it's actually going to converge.
So that means the majority of functions diverge?
Well, it's hard to
Is it
talk
kinda
about
like half and
majorities
half?
when you got infinities of possibilities going on. All of the interesting ones that we use converge, but there are a whole lot more than just the interesting ones that we use. You know, so that's a tough one for me to quantify. Yeah. All right. But let me just talk about a couple of these tests.
You explained what the test was and how to do it, but you didn't explain why it works.
Right. That's a really good point. And so one of the differences between what we do in here and what we do in a class called analysis. In analysis, what you do is you go back through every one of these theorems and you actually prove step by step every one of these theorems. In Calc 2, we just present the theorems and show you how to use them. That's what the distinction is. And in fact, it's not that I'm skirting it. You'll see that they're not, the proofs aren't even in the book for the most part. Some of them are. Like I think I did show you the one where there was the absolute convergence theorem for sequences, like that one I proved. But a lot of these require days to prove. I mean, it's not days, but like when I took analysis, it was probably like 3 lectures to go through and prove some of these convergence tests. So that's not what we're going to be doing here. I'm just going to present them to you and show you how to use them. That's the idea.